Earth Calling Dynamics class. Earth Calling Dynamics class. Uh-oh. Don't like the looks of this. I want to see my whole whiteboard and I'm only getting part of it. Dang it. Maybe I could move it over. Let's see. Yeah, there you go. Okay. I think I need to tilt this like so. That's pretty good. Is there anybody out there? Earth Calling wonderful students. Come in, wonderful students. I don't hear any happy voice. Hey, there's Kristen. You can count on Kristen. Hello, Kristen. Click to share screen. Yeah.
Good morning.
Good morning.
How are you?
Oh,
Huh?
I'm fine today. How are you?
I'm sleepy.
I was sleepy yesterday for one of my classes.
Yeah, thermo. I was sleepy then too.
I was real sleepy, but I got some sleep last night.
I didn't. I couldn't sleep.
Well, that happens to me every night from about 1:30 to 3:30 I couldn't sleep. But that happens every night.
Yeah, I couldn't sleep and I kept trying and finally about 3 o'clock in the morning, 2:30, 3 o'clock in the morning, I took some Tylenol PM to try to help me go to sleep.
Yeah.
And then I didn't want to get up though.
Well, maybe you could get the audio of my lecture and play it.
Oh no, I'm just gonna. I watched one you had last week.
Okay.
On Thursday, because I watched Keziah's graduation.
Oh, okay.
Online, so I was able to get on there and play it and stuff, but I don't want to get behind. I like to do the lecture, do the homework immediately after, and
it's a good idea.
You did. I already uploaded the 2 assignments that you told us to.
Right.
Get those.
Yeah, I think one's due tonight.
Oh, I already did them. I did them yesterday.
Wow. But I put a new one on this morning.
For which class?
This one here.
For this one? Okay. Yeah. I haven't seen that yet.
Well, you'll find it, but it's not due till Monday, I think.
Yeah, I'll still do it today probably.
Yeah.
I just like to, I don't like to get behind on anything. I like to just do it when it's assigned.
I'm with you. Now let's see if there's anybody else that signed in.
Yeah, Dalton just signed in.
Dalton. Yay, Dalton. Good going, Dalton. Well, there's just the two of us. Well, we're going to study, let's see, what are we going to study today? General motion, Newton's second law, general motion, that's the topic. I guess we could write that. Newton's second law, general motion. That's what we're going to do. But if you had any questions, we got 4 minutes before class starts. I could answer a question. No extra charge.
I don't think I have one. I'm actually think I'm gonna go make a cup of coffee so I can quit
Yeah.
yawning.
Yeah, good idea. You go make your coffee.
Yes.
Hey, look
Let me
here.
do
I
that.
got Gavin and Sam. I got Sam too. Good going. Yeah, we're getting a good bunch here. Well, how about you guys? How about Sam or Gavin? Did you have any comments or questions there? Other than,
No. I do not.
no, that's fine. That's fine. Well, now, there was some homework. I think it's due tonight at midnight. Did you guys all get the word on that? Go to content, and there's some homework there. I forget which one it was. Let me look and see here. Yeah, it was review problem 17.3, and that was due, well, it's due tonight, I think. Yeah, and I'll post the answer, review problem 17.3. But since it's due tonight, I won't post it yet because I'm going to grade that. See, and I've learned how to do that now. And I've given a bunch of you that have turned it in a grade already. How about Eric? Eric, did you get your grade on that last R 17.3?
To be honest, I haven't looked yet.
Well, that's okay. No, there's no hurry. But I did grade quite a few of you. Several of you have turned yours in. Let's see. I've graded Caitlin and Daniel and Gavin and Eric and Ross. I've graded a couple more down there. So I've learned how to grade the homework on Blackboard. Isn't that neat? See, I can still learn stuff. Okay, well, hey, look, it's darn near 9:30. And I think maybe we should get started. Last call for any of your comments or questions. Okay, well, nobody, I didn't hear anybody. So let's see who else we got here. We got Allison and Alex. Welcome, you guys. What I thought we could do is work this problem 1798 to death. We'll just beat it till it hollers uncle. 1798, and it's on page 464 in your book. And I just thought we'd work it. Well, no, wait a minute. We're going to work 796 first, and then we'll work 797. What did I say? Seven? We're going to work 1796 on page 464, and then we're going to work 1797, and then we're going to work 1798. And then maybe we'll just play with that one all day today. Okay, that's the big plan. I think you can learn a lot from this. Okay. Well, let me start get started here. Now they gave us a radius of gyration, and I've told you guys about that. It's 0.3 meters. And if you remember, the way that works is the moment of inertia about G in this case, is equal to the mass times the radius of gyration about G squared. That equation defines the radius of gyration. And I tried to explain the radius of gyration the other day. And we're successfully putting these videos on YouTube, so you can watch them over and over till you get it. Okay, well, let's figure out this moment of inertia. Now it says it's 100 kilograms, and the radius of gyration is 0.3. So if you square that, guys, I can do that in my head. I'm getting 9 kilograms times a meter squared. We now have the moment of inertia about G. Now we're going to need the moment of inertia about A. In fact, here, let me draw the diagrams. You should draw 2 free body diagrams. Now, one of them is going to look like this. And the other one will be over here like this. A little bit messy there. I'm trying. Not too bad. Not too terribly bad. Now, what this is really a spool. It has an inner axis. Probably should put that in dashed lines, you know it, because you can't see it from the end. It's inside. It's like a spool. Well, in fact, that's what they call it. It's a spool. I think I should be able to make that prettier. There we go. Well, we tried. You need to draw 2 free body diagrams. One of them is the force diagram and the moment diagram. The other one is the kinetic force diagram, and it's the kinetic moment diagram. They're different. Okay, now if I only had some red pencil, my daughter's going to get me one. But if we're working 17, those of you that just tuned in, we're going to do 1796. Hey, there's an important person, Rebecca Griffin. Hello. And Sam, I think I already mentioned Sam. And there's Gavin. We got both Gavins. Good deal. Okay, this here is, if you read the problem, is 50 newtons. We have a 50 Newton force here acting on the axis, what do you call that? The recessed internal axis of your spool. You got 50 newtons doing that. Now let's get the other forces acting. And I wish I had a red pencil, but we'll do the best we can. Now what that is 100 newtons times 9.81. I'm going to do that in my head, but I'll write it out for anybody that needs it. I'm getting 981 newtons. Can you handle that? If not, just let me know. Never be ashamed to ask. Okay, well, then there's going to be a force here. Now, they call this a normal force. It's a normal force, and it's 981 newtons. And I think there's one more force. And this point here is point A. And this point here is point G. And then there's going to be some friction. Now, the thing about the friction, it's going to be going, well, either to the right or the left. Let me pick on one of my students here. Let's see. Am I muting everybody? Let me see what I'm doing here. Mute all, it says. Allow participants to unmute themselves. Okay, now you can unmute yourself. And how about my friend Eric? Eric always comes through for me. Eric, can you unmute yourself? And you got a 50-50 chance of getting this right, Eric. There's going to be friction here, but does it go to the right or to the left? Go for it, Eric. Say again.
I would think it would go to the left.
Okay, now Eric says it's going to the left, so he would put the friction that way. And Eric, you're wrong. But that's okay, because how are you supposed to know? Here's the thing: if you set up your problem that way and it turns out that you're wrong, you'll get a negative answer for that friction when you get all through, which means it's going the other way. But see, I've already done this problem and I know it's going this other way. But thank you, Eric, for trying on that. I mean, how are you supposed to know? Okay, so for right now, you're just going to have to trust me. But when we get through with the equations, I hope to convince you that the friction's going to the right. Now, pretend those are all nice and red. Pretend I had a nice red pencil there. There are 4 forces acting on that. But we don't know what the friction is. Don't know what that is yet, but we're going to get it here in a minute. Now, this diagram here is called the kinetic diagram. And what you have on that is the right-hand side of Newton's second law. So here let me write, see on the left-hand side of Newton's second law, you have the sum of the forces and you have the sum of the moments. On the right-hand side of Newton's second law, you have MA and you have I alpha. Put an equal sign there. The sum of the forces is equal to MA. And the sum of the moments, these are really vectors. The sum of the moments is equal to I alpha. And what this left-hand diagram is the left-hand side of Newton's second law. And what the right-hand diagram is the right-hand side of Newton's second law. So what you need to put right here is MA. There it is. And here you need to put I alpha. There's also a point A down here and a point G right there. Now we have drawn our 2 free body diagrams. Now what's going to happen to you maybe on your final exam, let's say, gosh, we only have what, 2.5 weeks left, something like that. What's going to happen to you if you only draw 1 free body diagram? What's going to happen? Let me think. Lose points. Lose points. That's what's going to happen. You're supposed to draw 2 of them. One for the actual forces and moments, and the other one for the, what do they call them? Kinetic moments and forces. 2 diagrams. You're not going to forget, are you? Oh, no, no, Mr. Griffin. We're not going to forget. Okay. Well, let's solve this problem then. Here we go. Why don't we do Newton's second? You realize these are both Newton's second law. It's just that one is for translation and one is for rotation. Okay, here goes. We're going to do this one now. The sum of the forces is equal to MA. Why don't we do it in the X direction, shall we? Because the Y direction is pretty boring. I mean, in the Y direction, you got 981 going down, 981 going up, and that's the end of it. But here in the X direction, we have 50 newtons plus your friction equals the mass times the acceleration. Now, see, that acceleration can be written like this. They said that this distance here is 0.4 meters. And we learned earlier, I don't know, January or February or March, somewhere in there, that A is equal to R alpha. I'll tell you where that comes from. It comes from, see if I can remember where it comes from. It comes from V equals R omega. I know you've used that equation there. V equals R omega. I know you've used that. And see, if you take the derivative of that, the derivative of velocity is acceleration. R is just a constant. It doesn't change any. The radius of this is 0.4 meters. And omega is the angular velocity. When you take the derivative of it, you get the angular acceleration. So see, we can substitute for A, alpha 0.4. Okay, great. We got too many unknowns. Right now, we don't know F and we don't know alpha. But we have some other equations. We got this one here. Sum of the moments about G is equal to IG of alpha times alpha. No, subtract that We do know IG, it's right here, see it? So let's write that equation. Here we go. Moments about, the moments about G. Well, this 981 doesn't give you a moment about G, it goes through G. And that 981, that doesn't give you a moment about G, it goes through G. But this 50 does. Now it'll be clockwise. I tell you what I'm going to do. I'm going to write these clockwise. It's my problem. I can do what I want. I'm going to write everything clockwise. Now what you got here clockwise is 50 newtons times, they said it was 0.25. This distance here is 0.25 meters. So you go 50 newtons times 0.25 meters. But now, wait a minute, we're not done yet. This friction here, that's going counterclockwise, so that would be a minus friction times 0.4 meters equals IG, which is 9, times alpha. Two unknowns. But they're the same unknowns. Look, This equation has F and alpha in it. And this equation has F and alpha in it. You know what? We have two equations and two unknowns, don't we? We could solve that. But being lazy, there's an easier way. Actually, that's not that hard. I bet you guys could do that. Tell you what, let's take time out. I'm going to show you an easier way, but let's take time out. Some of you need to wake up anyway. And you have two equations and two unknowns. Here, I'll box them up for you. You got this lovely equation here. And you got this one here. Two equations and two unknowns. Now I'm going to shut up for a minute and a half. We'll make it 2 minutes. Get your pencil and paper out. Solve those two equations and we'll get our answers. And I'm going to do it too. And let's see if we can get the same answer. Here we go. Well, I got an answer finally. Took me forever. Those of you that just tuned in, we're doing problem 1796 right now. And I've got the answer here for the alpha. And I'm checking, I did this before, and I'm checking to see if it's what I got before. And it is. Okay, here's what I got. I got alpha is 1.3 radians per second squared. And I want to hear an uh-huh. Somebody unmute and say uh-huh.
Uh-huh.
Hey, there's an uh-huh. Was that Ross? Who
No, that
was
was me.
that? Was Ross.
Nope, that was Alex.
Oh, that was Alex. Good going, Alex. Proud of you. I need another uh-huh. Somebody unmute and give me another uh-huh.
What I got? This is Ross. Uh-huh.
I think that was two different uh-huhs right there. Hey, we're doing good. We've got our alpha now. And now we can get our linear acceleration. It's just 0.4 times alpha. So let's do that. I can do that. 0.4 times 1.3. 0.4 times 1.3 equals 0.52 meters a second squared. I wonder if that's what I got when I did this before. It has to be, but acceleration, blah, 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 blah. Yeah. Boy, Jove. We're doing good. Hey, you know what? We can get our friction now. Now, if this friction comes out plus, it's going to the right like I said it was. But if it comes out minus, then my excellent student, I forget which one it was that said it was going to the left, they'll be right. But we're going to find our friction now. So you can get that from either one of these equations, right? Because they both have friction in them. So here we go. We're going to get our friction now. Here goes. And let's see. Well, I'm getting 2 newtons. I wonder if it works in both equations. Let me check that. They call this checking your work. See that friction, if it's 2, it ought to fit this equation too. Let me see if it does. 50 times 0.25 minus that. Boy, Jove, that equation works too with the same F's and the same alphas. And it came out plus. So the friction is, it turns out the friction is 2 newtons going to the right. To try to explain that, it helps if you think what would happen if this surface here, it's hard to draw a straight line. It's supposed to be a smooth, if it didn't have any friction, if it was like somebody put some oil on it, maybe, then this thing would have a tendency to slide, wouldn't it? Yeah. So, well, that's a bad example because if it's trying to slide, the friction would be going to the left, and my students' thinking would be intelligent. But another way to think about this is if you pull on this 50 newtons here, this thing tends to rotate. And so this surface here of the spool is trying to turn clockwise, going to the left. So that makes the friction going to the right. So I didn't explain that too good. But Newton's second law gave us the answer. We know the friction's going to the right. We've got all of our values. We got our alpha and our linear acceleration. See, alpha is rotational acceleration. A is linear acceleration, and we solved the problem. And hey, we could even, I was going to say we could look up the answer, but we can't because it's got a little asterisk on that problem. But we're going to do 1797 and 1798 next. But first, I want to show you an easier way instead of having to do 2 unknowns with 2 equations. There's an easier way. Here, let me, you guys have all this information. I just need some room here to operate. I want to show you an easier way here. There's an equation that goes like this, where you take the moments about A. See, A is this point down here. A is actually called the ICZV. It's the instantaneous center of zero velocity. at A, this thing's rolling. And so there's no relative motion between the spool and the surface. And there's an equation that goes like this. It's Newton's second law. It's just written in a different fashion, that's all. I've given it to you before. It's in your book, only they disguise it, make it more complicated looking. But see, this term here, in this case, drops out because you see the acceleration of that point A on the wheel there? This term is 0. There is no relative motion between the spool and the surface. And so the acceleration of A is, you could think of it as 0. Now, I'm lying to you a little bit because the acceleration of point A on the wheel does have an acceleration, and it's towards the center. And they have a name for that. They call that centripetal acceleration, and you know about it. It's just that this R is going from A up to G, and the acceleration of A is centripetal. It's going from point A up to G. And when you take a cross product of vectors that are in the same direction, you get 0. Because the cross product has a sine of an angle, and that angle is 0 if they're in the same direction. So see, this term drops out. We don't need it. And all we need is this one here. Well, we never did get the moment of inertia about A, so we're going to have to do that. Come up here with me. And let's do that. That's going to be IG plus 100 kilograms times the distance between A and G. Now there's A, there's G. The distance between them is 0.4. We're going to have to square it. And when you do all that, you'll have 9 plus 100 times 0.16, that's 16. You're going to get 25 kilogram meters squared. All right, here we go. We're going to take the sum of the moments about A now. And about A, this 981 goes through A, so it doesn't give you a moment. This 981 goes through A, so it doesn't give you a moment. The friction goes through A, so it doesn't give you a moment. The only thing that gives you a moment is the 50 newtons. But what's the distance? Hey, I'll pick on Daniel. Daniel, unmute and tell me the distance for that from A up to that 50 Newton force, Daniel. Go for it. Earth calling Daniel, Earth calling Daniel. Come in, Daniel. We need the distance from A up to the 50 Newton force. What is that distance, Daniel?
Is it 0.65 meters?
Good going, proud of you. Exactly. It's 0.65 meters. Daniel is right on the money. And then we just did that. It's 25 kilogram meters squared times that. Oh, look, one equation with one unknown. That's easier than two equations with two unknowns, isn't it? Oh, yeah, yes, it is, Mr. Griffin. All right, well, I'm going to do that. You do that too and see what you get. By the way, for those of you that just tuned in, I put a homework assignment on Blackboard for you guys. I think it's due Monday. What's today, Wednesday? I bet you can get it done by Monday. You'll see it there. It's on Blackboard. And I've learned how to grade your papers. And I've graded a bunch of you already on this last assignment that's due tonight. There's no big hurry. You don't have to get it in till midnight tonight. It's on Blackboard. Okay, I'm doing this now. And here's what I'm getting. I'm getting alpha is 1.3 radians per second squared. Hey, Shazam. You know what? That's what we got for alpha when we had our two equations and two unknowns. Yay. And once you get alpha, of course, you can get the linear acceleration, and with that, you can get your friction from Newton's translational second law. You get all your answers a lot easier, I think. Okay, we're gonna travel on now. We're gonna do the next little project. We're gonna do is 1797. Now it's got answers in the back. Isn't that nice? But we don't need no stinking answer book because we can check this stuff ourselves. We can check it ourselves. We've already done this problem 2 different ways and got the same answer, so we know we're right. Okay, if you're happy, I'm gonna erase some stuff so I can have room to work, and we're gonna do 1797. I'm waiting for any comment or question. So I guess you're happy with it. All right, here goes. We're just going to get rid of some of this stuff because I need the room to operate here. Now this is pretty boring, but my thinking is boring is good. If you're bored right now, that's good, because that means that you understand this so well that you're just bored. And that's what I want. I want you to understand it so well. Okay, now what we're going to do now is we did that. Check. Put a little check mark there, and we're happy with that. We're going to do 1797 now. I need that room. I'm going to get rid of that too. I already got that figured out. You got all this stuff written down in your notes. I know you guys are taking excellent notes. You guys are taking excellent notes. All right, well, let's see what this 1797 is. Ooh, it says the 50 newtons is vertically upwards. Ooh, that's a different story. Well, let me try to draw these two. Let me try to draw these 2 diagrams now. Well, I tried. Okay, there's my 2 diagrams. But see, the way I understand it, the 50 newtons now, I'll do these dashed because this is it's the axis of the spool. There's G, there's A. But I think what they're doing now is they're pulling, they've got the 50 newtons, it's pulling straight up. That's what it says. Look, read it. It says directed vertically upwards. Okay. All right. Well, now we still have the 981 and the 981. And we got the 50 newtons now, but it's going straight up and we have friction. Oh, but gosh, I don't know which way this friction's going to go. Let's go to one of my excellent students here. We've got two Gavins. I want Gavin Shepherd. Gavin Shepherd, unmute, and I want your thinking of friction going to the left or to the right. What do you think, Gavin?
I believe it's going to be going to the right.
Okay, Gavin says to the right. And to be honest, I don't remember whether it's going to the right or not.
Well, if you do the instantaneous center of velocity, wouldn't that point to the right direction?
Well, I tell you what's going to happen. It's going to rotate clockwise. Is that
Right.
Is that what you're saying?
Right. So because it'll rotate clockwise, it'll be going to the right.
You know, I think Gavin's right. He's convincing me. Because the sum of the forces is equal to MA, and I believe in support of Gavin's idea, the MA is going to the right. If it rolls clockwise, it's going to go to the right. And if the right-hand side of this equation is going to the right, then the left-hand side of this equation has to go to the right. Well, the only thing that can go to the right is that friction. There isn't any other left-right, is there? Gavin, you got me convinced. It's going to the right. Good going. Okay. Well, we have that equation. You could put in the, you could write it like this, friction, which we don't know, is equal to 100 kilograms times alpha r. You could go alpha 0.4 meters. See, but here's the problem. You've got the same doggone problem. We don't know what F is and we don't know what alpha is. I meant to talk to you a little bit about that friction. See, they said that mu sub s is 0.2. We just sort of neglected that. And mu sub k is 0.15. And it's rolling. Now, when it's rolling, you're dealing with static friction. See, if it's slipping or sliding, you're dealing with kinetic friction. But this spool is rolling, and there is no relative motion between the spool and the surface. See, there's a surface here. And so, what was I going to say? It's rolling. When you're rolling, you use static friction, and the way that works is static friction is less than mu sub s times the normal. Now, we're going to solve this problem. I forgot to tell you about that in the last one we did, the 1796, but we'll talk about it on this one. We're going to solve for the friction, and we're going to see if it's less than the static friction coefficient times the normal. I can tell you what this is. This is 0.2 times 981, and that is 0.2 times 981. That is 196.2 newtons. And you're going to find that the static friction is going to be much less than 196.2. We're going to solve for it here in a minute, and you'll see that we're in great shape. Okay, well, let's solve it. There's a little talk to you about friction. Now, I showed you that lovely equation here just a little while ago. It goes like this. Remember, there was another term. There's another term, but we don't need it because that point A doesn't have any horizontal acceleration on the wheel. It's rolling, and it's got the zero velocity there. Anyway, I tried to explain that. And so we're going to solve this. It'll be easy. Here we go. Sum of the moments about A is, well, the 981 doesn't give you a moment about A. It goes through A. And the 981 doesn't give you a moment about A. It goes through A.
Yeah, isn't it just the 50 newtons in the radius?
Yeah, good going. It's 50 newtons. Friction doesn't give you any moment about A either because it goes through A. So it's 50 newtons. Now it's going to be clockwise. You can see it. We're writing this equation clockwise. See, you've been taught that clockwise is negative, but they would both be negative, and so algebraically just call them both clockwise. There we go. Times 0.25, I believe they said. I forget. Is this distance 0.25? Read it. Yeah, it's 0.25. This distance here is 0.25. And so that's it. That's all the moments that you have. And we just did that. It was 20. I think I erased it, but didn't we get 25 a minute ago? Those of you that are taking excellent notes. Hey, we can get our alpha now. Here goes. Get your calculator. Solve this for alpha. All right, 50 newtons times 0.25 divided by 25. Did you get an alpha of 0.5 radians per second squared? Hey, you know, that's bigger than the other one. What was our alpha on the other? It was 1.3. Do you guys remember? It was 1.3. But this alpha is bigger. Wonder why it's bigger. I don't know. Newton doesn't lie. Okay, now we're going to find out.
Not bigger.
I'm sorry, what?
Alpha
No, I'm wrong. I didn't write it. I didn't write it. You're absolutely right. 0.5 is smaller than 1.3, isn't it? Yeah.
This is big brain time right here.
I'm sorry, what?
Nothing. We're just making the really esoteric observations right here.
You guys are so smart. Before, we got an alpha of 1.3, but now we're only getting 0.5. And I think I understand, because see, when the force was going to the right, kind of makes sense that it goes faster than if you're pulling straight up. I'll go with that. And now let's get the linear acceleration. How do you do that? You go 0.5 times 0.4 Now, this is the acceleration of your center of mass, and I'm getting 0.2 meters a second squared. Okay, and now we can get the friction. Here we go. Now, if it comes out plus, it's going to the right, like my student said. So I guess you could just plug in this here, that would work. Here goes. Did you get 20? I'm getting 20 for the friction. We think the friction is 20 and it's plus 20, so it's 20 newtons to the right. What was the friction last time? I forgot. Last time, the friction was, I can't find it.
It was 2 Newton.
Yes, good going. Thank you. It was 2 newtons, and now it's 20 newtons. Man, it went up, didn't it? But you know what? It's still less. The friction is still less than the maximum possible friction. Remember, the maximum possible friction is equal to 0.2 times 981, whatever that is. And 20 is less than 0.2 times 981, isn't it? What's 0.2 times 981? Times 981. Gosh, I'm getting 196.2 newtons. The question is 20 smaller than 196? Well, yeah. So we're still rolling. We're rolling. We've got static friction. You got to be careful with static friction because it's an inequality. It's not an equality like kinetic friction is. Okay, hey, now there's answers in the back. I'm going to go to the back of the book now and see what they said. We just did 1797, and I'm looking up what they said. They said 1797, they said alpha is 0.5. That's all they said. Well, that's what we got. Yay. Well, let's go on. We just did 1797. Now we're going to do 1798. But first, let's pause and see if anybody has a comment or question there. Well, I didn't hear anything. I guess you're all okay. We know we got right answers. We have no doubt. But I want to show you another way of checking your work here. Let's see if there's any room I could fit in. Here, let me fit in. I'm going to check my work here. Now, I'm going to circle these two equations here. And I'm going to erase all that other stuff because we understand it, or I hope we do. Yeah, I got some room I can operate on here. Now these two equations, they have a name. I'll give you a hint. It's it's and I'm going to pick
Newton's second law.
Yeah, there you go. It's Newton's second law. Exactly. These equations, but there's two more. Let me write those too. There's two more. One of them goes like this. It'd be fun to do those as just as a check, see, in case you want to check your work sometime. Yeah, the other two, I think I've already, well, I've written them, but I don't think we actually used them on this one. But we can. That'd be fun. Those are the other two. All four of these are different forms of Newton's second law. This one is translational, and this one is rotational. Now we've done both of those, but we haven't done this one. I don't know if we've done that one. Here, let's do that one because I got a little room here, and then we'll do that one here in a minute. Okay, here goes. Now what we're doing right now is something that I introduced a number of semesters ago. It's called checking your work. Well, one of these days, you're going to be out with a job someplace, and you're going to be figuring out something. And there's not going to be anybody, there's not going to be any Mr. Griffin to help you. There's not going to be an answer book that you can look up the answer with. You're going to have to make sure that what you're doing is right. And I tell you the truth, people out there sometimes get sloppy and they make mistakes, and it costs money. And it can even cost more than that. It can cost lives if they screw up. So it's called checking your work. It's a good idea. All right, here goes. Some of the moments about G. I'm going to do it clockwise again. Now we got the 50 newtons times 0.25. Hope you can read my writing. 50 newtons times 0.25. I'm doing this equation right here. Meters. But I'm not done yet. If you're writing clockwise and the friction is 20, you're going to have to go minus 20 Newton times 0.4 meters equals, we did this before, I think I erased it, but remember it was 9 kilogram meters squared times alpha. We're doing this equation right here. It's called Newton's second law for rotation. We have just written it, and we're going to solve for alpha and see what we get. Here it goes. You do it and I do it. Go ahead, get your calculators out and do it. Go for it. Well, I got an answer. I got 0.5 radians per second squared, but I'm going to wait. Yay, good. I need a couple of more uh-huhs out there.
That's what I got.
Yay, there's another one. How about my friend Allison? Allison, unmute and tell me when you get that.
I got that.
Yay, good going. Hey, we just checked our work because that's what we got using a different equation, huh? We didn't use that equation. We used a different equation to get that. Okay, great. We just checked our work. Now we're going to check our work with this equation here. Let's do that. I'll wait though if anybody hasn't quite finished. Okay. To repeat now, there are 4 versions of Newton's second law. There they are. They all have to work. So far, we're doing great. Now I'm going to do this one here. Let me make a little room here and we'll do that one. And what we're doing right now is we're double checking our work. We're double checking. Okay, moments about A. Well, this 981 goes through A. It doesn't give you a moment. And the 20 newtons friction, that goes through A. It doesn't give you a moment. The 981, that's the weight of the spool. It goes through A also. The only thing that gives you a moment is the 50 newtons times 0.25 meters clockwise equals, now IG, if I remember right, was 9 kilogram meter squared times alpha. And this R here, we're talking about the R that goes from A to G here. Here, I'll draw it for you. There it is. That's that R. It's 0.4. And the mass, I'm running out of room here, the mass is 100. And AG is alpha times 0.4. Okay, get your calculators and solve for alpha using that equation. On your mark, get set, go. I pushed the wrong button. I got to start all over again. Boy, Jove. I'm getting alpha is 2 radians per second squared. Is that the right answer? Is that what we got before? I don't remember. Was it 2?
I think it was 0.5.
Okay, I must have done something wrong. Now let me check this. Moments about A. No, I think we did that right. I think that's a moment about A. And then this here's 9. And R is 0.4. Mass is 100. And acceleration of G is alpha times 0.4. Okay, well, let me try it again. I must be doing something wrong. Oh, I pushed the wrong button. I'm getting 0.5 this time. How about you guys?
Yeah.
Yay.
Yeah.
Well, good. Well, guess what? That's what we got using different method. And so we're quite confident that we got 1797 done. Okay, well, good. Let's move on. I'll wait a minute if anybody has a comment or question or needs to catch up with us. We're going to do 1798 here in just a minute.
Can you read off the last half of your equation? It's kind of hard for me to see.
Oh, yeah. My writing isn't that great. Well, this is 50 newtons times 0.25 meters. This is 9 kilogram meters squared times alpha. And this is 0.4 meters. I didn't write the meters. I ran out of room. There's 100. That's 100 kilograms. and I wrote the linear acceleration is alpha times 0.4.
Okay.
You okay?
Yep.
Thank you for asking. It worked if you can read my writing. Well, let's bore you some more and do 1798 now. I told you we were going to just work this problem to death. All right, here goes. We got that done. Yay. I'm thinking that you guys probably are with me now and you got the hang of this. And maybe I can do something else rather than 1798. What's different about it? They upped the they just upped the force is all, and they have answers in the back, and you guys could do that, but I'm going to do something kind of interesting here. And just a minute now while I get organized here. Instead of doing 1798, which I promised, but see, I'm looking at the clock here, and I don't think I got time. But I have confidence that you guys can do it. The answers are in the back. But instead, what we're going to do is we're going to change the problem and make it very interesting. We're going to make it very interesting. Here we go. Now, how many free body diagrams are you guys going to draw for me on these problems? How many? You're going to draw 2 free body diagrams, aren't you? One for the actual. That circle isn't very. Let me try that again. That circle wasn't very. I wasn't very happy with it. That's a little better. Okay. How come that circle's smaller than that one? They're supposed to be the same. Oh well.
Artistic interpretation.
little artwork here. Okay. Here's what we're going to do. We're going to put a honkin' 5,000 newtons on there. Here's G. Everything else is the same. We haven't changed IG. It's 9. We haven't changed IA. It's 25 kilogram meter squared. We haven't changed these distances. This is 0.4. But we haven't changed this normal force. It's 981. We haven't changed this normal force. It's not a normal force. It's the weight. But we're going to put a honkin' 5,000 newtons on there. And now the friction, man, it's been going to the right every time, hasn't it? Every time we've done the friction, hasn't it been going to the right? My guess is it'll still be going to the right. Well, I forget, was it going to the right? Yeah, it was going to the right. Okay, and so this diagram here, you're going to have an MA and an I alpha. All right, there's the information, and we're going to solve that now. Why don't we start with this equation here, since we know and love this equation so well. Remember, there's another term, but if it's rolling, that other term disappears. If you don't understand that, ask me, I'll go back over it. All right, here goes, moments about A. Clockwise moments, we got 5,000. And one of my excellent students, I think it might have been Coy, I'm not sure. But whoever it was figured out it was 0.65. And that's it, we're done. Equals 25 times alpha. Okay, we can solve for alpha. Now, if you have any questions about that equation, you don't understand it, just speak up, unmute yourself, and ask me. But I'm going to go ahead and get that alpha now. I'm getting an alpha of 130 radians per second squared. And now, see, you can get your linear acceleration by going A equals R alpha. So multiply the 130 times 0.4. Gee whiz, I'm getting 52 meters per second squared. I wonder if that's what I got before. Let me look and see here. Boy, Jove. Oh, yeah. Yeah, that's what I got, all right. Okay, now we're going to get the friction. Now the way to get the friction is you go sum of the forces equals MA, right? Yeah. And the forces, you have 5,000 newtons plus the friction equals 100. And if it's rolling, this would be 0.4 times alpha. No, you don't need to do that. You can just go 52, right? Am I getting mixed up? I'm getting. No, I'm not getting mixed up. It's 52. Here we go. And see, you can solve for friction. If I lost anybody, just speak up and I can slow down. Now I'm going to get my friction. Here we go. Gee, I can almost do that in my head. Are you getting a friction of 200 newtons?
Yes.
Yay! Well, I don't know if you remember this, but the maximum possible friction that you can get is static friction. And it's, what was the coefficient of static friction? I got lost there. It was 0.15, no, 0.2. It's 0.2 times the normal, which is 981. So the maximum possible static friction that you can get is 196.2 newtons. Uh-oh. We solved this and we got 200 newtons. You can't get, guys, you can't get 200 newtons. The biggest friction that you can ever get, they have a name for it. It's called impending. Impending motion is when you run out of static friction and you start slipping or sliding, and you're into kinetic friction. So we have just discovered the maximum possible friction is 196 newtons. And if it's rolling, we need 200 newtons, and we don't have it.
So does that mean that it's sliding?
Yes. Actually, what it's doing is slipping. There's a slight difference between slipping and sliding. In your automobile, when you slam on the brakes and you skid, they call that sliding. In your automobile, when you mash the accelerator and your wheels lay rubber, they call that slipping. Slipping is your accelerator, sliding is your brake. This thing here is slipping. It's kind of like somebody's mashing on the accelerator. See that 5,000 newtons? That makes that thing want to spin so fast that it's laying rubber, so to speak. So what we have discovered is it's not rolling, and you can't use static friction. You have to use kinetic friction. So all of this stuff that we've just done is all a bunch of bull. And we're going to have to start over, and we're going to have to use kinetic friction. See this equation here? It's no good, because remember, there was another term. Do you remember there was another term? And it had the acceleration of point A on your spool, and it's got an acceleration. It's spinning so fast clockwise that there's another term. This equation is no good anymore. I don't know if I told you that, but this equation here has a skull and crossbones on it. And now is as good a time as any for you to know about it. They have this equation in the book. It's a lovely equation. It works great if you're rolling. But if you're slipping or sliding, you need that other term that I wrote. And so now let's do the problem. Let's solve this problem. Here we go. I just need some room now. All this is wrong. The frictions, that maximum friction is correct, but the friction that we got, the 200, is not correct. So I'm going to erase all this stuff that didn't work. And we're going to solve the problem and find, well, what we're going to do is we're going to find the actual friction, and we're going to find the actual acceleration of the center of gravity, and we're going to find the actual angular acceleration. That's what we're going to do. Okay. So where do we start? Here's where we start. Since we know it's kinetic friction is equal to the kinetic coefficient of friction times the normal. What was the kinetic coefficient? If you read the problem there, it's 0.15. So this is how you get your friction. But you had to go through all that other stuff first to find out that it wasn't rolling. How come this is flat on the bottom? Does that tire have a flat? Is that what happened? Okay, here's the actual friction. It's 0.15 times 981. We have 147.15 newtons. That's the actual friction. Yay, we got that done. Let me circle that. Now we need to find the acceleration, the linear acceleration, and the angular acceleration. Well, let's see how we're going to do that. How about this? The sum of the forces acting on this spool is equal to MA. We're going to do it in the X direction, guys. So what we got here is 5,000 plus 147.15. I'm getting 5,147.15 newtons going in the X direction. There's your mass. And now we can get our linear acceleration. Here we go. Did you get for the linear acceleration of 51 point blah, blah, blah meters a second squared? So we got that. Look at here. We got that. Ta-da. Now we're going to get alpha. Now you can't use this. Remember this lovely equation here, A equals R alpha? That equation works great if you have an ICZV or a fixed pivot. You know, if you have an R and an alpha, it works great. But see, it doesn't work here because you're slipping. That equation works for rolling. You could put a skull and crossbones over it if you wanted. There you go. That equation does not work if you're slipping, but we do have an equation that does. I just need room to write it. I see some room up here that nobody's using. Let's try that. There's all kinds of room right there. I don't need this stuff either. Now you should do 1798 just for your own enjoyment. And I know you can do it. I believe in you. Okay, well, how are we going to get this alpha? We got these, the friction, we got the linear acceleration alpha. How about we use one of our Newton's second laws? How about we use, this one's a good one. There's no skull and crossbones on that equation. You can put a happy face on that one. There's no skull and crossbones that I know of. Okay, let's do it. Well, what you got in the moments about G, you got a 5,000 times 0.4 clockwise minus, we know what the friction is, we solved it. It's 147 times 0.4. This is wrong. Somebody could have gotten a thank you point. It's 0.25, isn't it? Hey, there's no thank you points. A perfect lesson. Look at that. 0.25 meters minus 147 times, that's times 0.4 though, equals IG. Now IG, I believe, was 9 kilogram meters squared. Hey, we can get alpha from this. Okay, go ahead with me and we're going to get that alpha. Hope you can read my writing. Here it is. 5,000 times 0.25, 147 times 0.4 divided by 9. Did you get an alpha? I wonder if this is right. 132 point, I don't know, let's round it off, I guess. Let me see if that's what I got when I did it before. Alpha, yeah, that's what I got, all right. Yep, and that's what I got for the AG. Yeah, I think we did this all right. Hey, we could check our work, but I'm kind of running out of time, and I'm getting tired of this problem. I don't know about you, but I am getting tired of it. But let me show you one last thing here. I want to show you that this equation here does not work. We've got our 51.4715, 51.4715. What I'm trying to tell you is that is not equal to 0.4 times 132.35. 132. This equation does not work if you're rolling. It works if you're rolling. If you're not rolling, it doesn't work. Okay, I'm going to plug that in and see if it's not equal. They better not be equal. They're not. This here comes out to be 50, close to 53. They're not equal. This equation here, it only works if you're rolling. Well, I've done all I want on that problem. I am very tired of it. It was fun though. And I want you to, this is not official, but I want you to do that third one. What was it? 1798, just for your own enjoyment. But there is a homework that I've assigned. It's due Monday. And it's on Blackboard under I think you go to content, assessments, and assignments. If you're lucky, you'll find it. I can tell you roughly what it is. It's 1778. It's on page 453. And that's your homework. Okay, well, we've had a wonderful time together. And this is your chance to ask me any comment or question there. And if you don't have anything, I'm going to click this button that says end session if I can find it. But I'm listening. I'm listening for any comment or question. I didn't hear anything. Okay, I tell you what's going to happen to students that don't ask me any questions. We're going to click on something that says end meeting. This is your last chance. 5, 4, 3, 2,
All right,
1.
Professor, I'll humor you.
I'm sorry, what did you say?
I said, all right, Professor, I will humor you.
Okay.
All right. So, you know how earlier, I believe it was the third problem we did, you had the force being directed upwards
Yes.
that was causing the rotation?
Yes.
Wouldn't that change the normal force that was acting on it from the ground?
Oh, that's muy inteligente. I need to give that student a thank you point. It will change the normal force, won't it? Yeah, absolutely. It'll change the normal force, but I still think the friction will be rolling. It'll make the friction even smaller, won't it?
Yes, it would.
Well, let me put it this way. No, the friction, I think the friction we got is correct.
But it had the possibility of not being correct.
I wish you'd spoken up, but that I hadn't thought of that. But I don't think it changes a thing about the way we did that problem. What it changes is when you calculate the maximum possible friction, It's,
Okay.
it's equal to the mu sub s times the normal, and the normal will be different. You are
Okay.
right. But
But we
see,
got the right answers, so
yeah,
we didn't need to worry about that. But if we had a larger force, then we would have needed to worry about that.
yeah, I guess it's, what would be fun if we had time is take that 5,000, 5,000 newtons and go up. But you know what would happen?
It'd
If
fly up.
it'd be like a yo-yo. It would not go to the right. It would go up like a yo-yo, wouldn't it?
Yes, Professor.
Yeah. But no, we didn't, I didn't put any wrong thing up there, but you're absolutely right about that normal. Well, I was wrong about the normal. The normal would have been smaller, wouldn't it?
Yes, so the friction force would have been smaller. But we got the right answer, so which means that it was below the threshold of the new normal
That's
anyways.
correct. That's correct. What was that force going up? Was it 20
Uh,
newton?
I thought it was it was either 20 or 50.
I don't remember. Let me look and see here. That's an excellent comment. I'm proud of you. No, I can't. I think it was 50, wasn't it? Yeah, 50. I got lost here. My papers are all mixed up now. I tell you what, I could look in the book. The book knows what it is. It was 17. Anybody know what page it's on? Okay, I'm getting there. Yeah, there it is. It was 50. It was 50 newtons.
So the normal force would only have been like 48 newtons.
That's right. It would have been, well, no, it would have been 981 minus 50.
Oh, okay.
Are you with me on that?
Yeah, so it would have been like 860.
Yeah, it'd be 800 and something. Yeah. But we didn't, other than that, other than writing the wrong normal force, but I'm proud of you. You're absolutely right. Good. Okay. Back to the class now. I'm going to push this little button that says end meeting, but 5, 4, 3, 2, 1. Okay, I'm pushing it. Bye-bye, you guys. See you at, well, I'll see you next Monday at 9:30, right? Yeah, that's when I'll see you. Okay, end meeting. Bye-bye. End meeting for all.